Okay, we are recording. So now we're going to look at spherical coordinates. Spherical coordinates. And remember, well, if we think about spherical coordinates, okay, so if you have a point in space, okay, the spherical coordinates are rho, phi, and theta. So the angle theta is measured from the positive x-axis in the counterclockwise direction like you're used to. Phi is measured, that angle is measured from the positive z-axis downward, and phi is restricted between 0 and pi, 0 and 180 degrees. Theta goes from 0 to 360 degrees. And then rho is measured out from the origin. And so this is how you can locate any point in three-dimensional space with a radius rho and an angle theta and an angle phi. So based on that, what would the let's say this the right way, what would the volume element be in spherical coordinates? Well, what they do is, of course, they have a picture here in figure 7 that details a volume element from a solid using spherical coordinates. And of course, if you think about base times width times height, and think about the think about that volume element in terms of that. It's an approximation, right? The volume, base times width times height. That's how I like to think of it. It's just I'm not saying it's like the actual proof of the volume element. Well, I want to say this the right way. Let me say it the right way. So we'll go back to that picture. But if you're going to use spherical coordinates, then you're going to replace x, y, and z with the definitions of what x, y, and z are in spherical coordinates, and dv is equal to rho squared times sine of phi d rho d theta d phi. Okay, that's what let me just see here, one moment, class. Yeah, that's what it is. Now, in terms of the figure, here in figures, hold on, I don't know why that's up. Let me get that off. Yeah, in terms of the figure, that volume element, if you look at the length, width, and height, so like the delta rho, that's pretty clear. That would give you length. Width would be equal to rho times delta phi. That's not as well. Delta phi actually, no, that's okay. Delta phi, to be honest, I'm wondering if there could be a typo in this picture, because delta theta should be your arc, for this, and they have delta phi. So I'm going to look at this a little more on my own, but let's just for now, I was looking at this actually when you were working on your classwork. For now, just take it on faith that the dv is rho squared sine of phi d rho d theta d phi. That's what your dv is. So let's look at a problem here, and I'll try to get back to you on this on the next lecture regarding that volume element, how they get it, because I'm not completely satisfied that there maybe isn't a typo there. All right, but let's let's go right here to this example, okay? Let me give you a moment to copy this example down. Okay, so in this problem, we want to find the volume of a solid that lies above the cone, positive part of the cone, and below this sphere. Now, sometimes when you have a sphere, well, of course, a sphere, spherical coordinates work great with spheres. And here you have a cone. Sometimes you can use cylindrical coordinates as well for problems. Like what I'm trying to say is you could have a problem where rectangular coordinates don't work, but cylindrical and spherical coordinates will work. On this problem, I decided, and it's actually an example from the book, but they use spherical coordinates for this problem. And I've not tried to do integration using cylindrical coordinates because I think spherical coordinates based on the geometry of the problem are going to work much better. But that being said, what would be helpful to start this problem off? I mean, we have to get our limits, right? Our limits of integration. So what would be almost essential to have in order to help us with that? A sketch. We need a sketch. Okay, we need a sketch. That's right, Robin. Good, good. So I'm looking here at this sphere. Would this sphere be centered at, and this here is a Z on the right-hand side. This is a Z here. Would this sphere be centered at the origin? What do you think? I mean, if we had taken an analogy here, if we have x squared plus y squared plus z squared equals 16. This is a separate thing here. This is a sphere. What's the center of that sphere? X squared plus y squared plus z squared equals 16. What's the center of that sphere? What's the center? What's the radius? That's correct, Ryan. The center is the origin. That's correct, John. The center is the origin, and that's right, Deodath. And the radius is 4. So, okay, fine. Now let's focus on the sphere that we're working with. Do you think the center is at the origin? What do you think? Tell you what, we could write this as x squared plus y squared plus z squared minus z equals 0. Writing it that way, do you think the center of this sphere is at the origin? Or definitely not? That's right, Robin. It's not. It's tempting to say it is, but because you're subtracting this z here, and I appreciate all participation, all answers, because the z is here, this cannot be a sphere centered at the origin. So let's find out what the sphere looks like. We go to the next page, and what I do is I bring the z over to the left side, and then I'm going to get the sphere in standard form. So I'm going to, from the fact that this is a 1 here in front of the z, okay, that 1 there, if you take 1, divide it by 2, and square it, you get a fourth. And that's how I determine that a fourth should go here. And z squared minus 1z plus a fourth is the same as the quantity z minus a half squared. How many recall this from way back, maybe section 9.1, where you learned this kind of thing, where you had some spheres and had to complete the square? How many recall that? To get the sphere in standard form. Okay, it's been a while though, right? It's been a while, but Robin recalls it. Well, then this means that we've identified this sphere, this equation. It's a sphere centered at 0, 0, and a half with radius a half, because the square root of 1/4 is a half. And so now what we're able to do is we're able to draw this picture here on the left of a solid E bounded below by a cone and above by a sphere. So let me give you a moment to get the picture down here, and then we'll talk about converting the sphere and the cone into spherical coordinates. They're equations into equations in terms of spherical coordinates. Let me give you a moment to copy that. Okay. So, okay. So now if we're gonna do the integration in terms of spherical coordinates, we have to convert we have to convert these equations of the sphere and cone so that they're spherical equations. So of course for the sphere, we know that by definition, we know that x squared plus y squared plus z squared is rho squared, and z is equal to rho cosine phi. So we end up getting rho squared equals rho cosine phi, hence rho is cosine phi. That's the spherical equation. Now, if the sphere were centered at the origin, you would have rho equals a constant, right? But the fact that the sphere, the center is at 0, 0, and 1/2, that's gonna make the equation of the sphere more complicated. Okay. All right. Now the cone, of course, it's a positive part of the cone because it comes up from the origin. Okay. The cone is z equals positive square root of x squared plus y squared. So what I do is I replace x with rho sine phi cosine theta and y with rho sine phi sine theta. That's the definition of x and y in terms of spherical coordinates. I square both of those terms, and I'm able to factor out from both terms here, I'm able to factor out a rho squared sine squared phi. That's a common factor. So rho squared sine squared phi is the common factor times then, so it factors as rho squared sine squared phi times the quantity cosine squared theta plus sine squared theta. Well, we know that equals 1. And so we're going to end up having the square root of rho squared sine squared phi, and that's just equal then to rho sine of phi. And we take the positive root because all of the z coordinates are positive in that solid E. So rho cosine phi equals rho sine of phi, but that means if we divide both sides of this equation by rho cosine phi, we'll get 1 equals the tangent of phi. Sine over cosine is tangent. Well, if 1 equals the tangent of phi, that means phi is going to equal, in this case, pi over 4. Okay, it has to be pi over 4. I mean, we know the tangent of 45 degrees is equal to 1. The tangent of 225 degrees also equals 1. But clearly, phi is restricted between 0 and 180 degrees. So phi is going to equal pi over 4, 45 degrees. And you can see based on the picture that if we highlight the rim here, okay, of the cone, we highlight the rim there, okay, highlight the rim of the cone. Well, every point, well, the rim, that is the cone, right? The rim is the cone. Every point on that cone, the one thing that's true is that phi equals pi over 4. And so that's the equation of the cone. And I note here also that for the sphere, well, yeah, okay. So are there any questions so far on this? Okay, very well. So now what we have to do Now what we have to do is we have to determine the limits on rho, on the radius. Well, in the picture, what I've done is I've drawn from the solid, from the origin, I've drawn here I don't know why that didn't, hold on, give me a line, please. I draw here a line segment going from the origin to the rim of the sphere, which is rho cosine, the sphere equals rho cosine phi. Okay, so all the points in the solid, okay, all the points in the solid would have values of rho that go from rho equals 0 up to rho equals cosine phi. That's the max. So therefore the limits, if we go to the next page, the limits on rho are going to go from rho equals 0 to rho equals cosine phi. Okay, those are going to be the limits. And similarly, I'll come back to this. If we think about phi now, the limits on phi, okay, well, phi here, phi is measured from the z-axis, okay, then phi axis, and then clockwise. So every point, okay, every point in this solid E, okay, has to have an angle phi that would range between phi equals 0, that would be for points on the z-axis, all the way to phi equals pi over 4 and anything in between. Okay, and so hence the limits for phi are going to go from phi equals 0 to phi equals pi over 4. And then for theta, well, theta, your limits are going to go from 0 to 2 pi. Okay, because that solid exists above all 4 quadrants. And so therefore, and of course it's volume. So volume, we have a 1 here. This 1 here is there because we're computing a volume. A volume always has a 1 there. And then, of course, this part here is your dV. Are there any questions on that? Okay, well, so again, what I like to do, I try to be consistent when I compute my integrals. I feel it helps me be accurate. I'm going to iterate. So I'm going to iterate the integral. I'm going to integrate with respect to rho first. That means the sine of phi is treated like a constant. And the antiderivative of rho squared is rho cubed over 3. So my inner integral, the antiderivative is rho cubed over 3 times sine of phi. And I'm going to evaluate that at limits of cosine of phi and 0. And when I do that, the integrand for my inner integral is going to be cosine phi cubed times sine of phi over 3. Let me give you a moment to catch up here. Let me know if you have any questions. Okay, well now this we're actually doing example 4 from the textbook, and example 4, you know, they when they work it out, they leave out they have like they leave out a few details in my view. I always you know, so like how are they going to get this antiderivative? How are they going to get this the antiderivative with respect to phi of cosine phi cubed times sine phi over 3? Well, they just, you know, magically, well, I want to say this the right way. Hold on, class. They say it equals negative cosine of phi to the cosine negative the quantity cosine phi to the 4th power over 4, and that is true. That is the antiderivative. But you know, for me, I like to do what's easiest. Okay, and for me, this reminds me of this is a substitution opportunity. Let u equal cosine of phi. Then du, it's a trigonometric integral. How many remember trigonometric integrals from calculus 2 when they took calculus 2? Okay, John remembers it. Yeah, let u equal cosine of phi. Du d theta is negative sine of phi. Du then is negative sine of phi d phi. And so negative du, that's a negative, negative du is equal to sine of phi d phi. And so I can replace sine of phi d phi with negative du. Cosine phi cubed over 3 is u cubed over 3. And of course, the limits, well, how do I get root 2 over 2? Root 2 over 2 is just, that's the cosine of pi over 4. Cosine of 45 degrees is root 2 over 2. And then the 1 here, well, that's just the cosine of 0. So you're going on that inner integral there, you're going from an integral with respect to phi to an integral with respect to u, just like you were trained to do. So I don't think it's, I really like to see the substitution, you know. I like to use it. I don't like complicated antiderivatives or antiderivatives where I have to think too long. If I can use a substitution to help me get where I need to go, I'll do it. And you should too, right? So, yeah, the 1 is just, hold on, let me make this a little nicer on the bottom. Whoops. Gotten a little better with this eraser. I kind of know how to use it now. Just got to move your hand real fast. Put it on white and move your hand real fast. So cosine of 0 hold on here. Man, let's do this again. Let's just do it again. All right, so root 2 over 2, that comes from taking the cosine of pi over 4. Because your top limit here was pi over 4. Okay, and then cosine of 0 is equal to 1. Took the cosine of 0 and I got 1. Okay, so now we have a double integral. Are there any questions before I go on to the next page? Who's ready to go to the next page? All right, John is, and Robin, Ryan, Christopher, marvelous, good. All right. Everybody's good so far? Dan is, all right. All right, well, let's go to the next page then. So you notice, by the way, that in this, when we did the substitution here, we have a 1, like, well, hold on, let me show it. When we did the substitution here, we have a smaller number for the bottom limit than we do for the top limit. But mathematically, that's okay. That's okay. It's no problem. When we go to the next page, I rewrite the integral. Okay, and you notice I do have a negative here, right? I do have a negative here. So if I absorb the negative in the integral, it'll cause the limits to switch. So the limits, instead of lower limit being 1 and the upper limit being root 2 over 2, the lower limit, when I absorb the negative into the integral, the lower limit is root 2 over 2 and the upper limit's 1. And that's more aesthetically pleasing. I like to normally have my smaller limits at the bottom and higher limits at the top. Okay. And now it's just, okay, well, the antiderivative of u cubed is just u to the 4th over 4. Okay, and I'm going to substitute 1 and root 2 over 2. That gets me down here. So we're finding a volume of, it looked like an ice cream cone, right? That's what we're finding the volume of. Okay, so here we are. Now, 1 to the 4th is 1, and root 2 over 2 to the 4th is just 4 over 16. In the denominator, you have 2 times 2 times 2 times 2 times 2 times 2 times 2. That's 16. And then in the numerator, root 2 times root 2 is 2. Another root 2 times root 2. 2 times 2 is 4. Okay, and so you're going to get 1 minus 4 sixteenths. That's going to become 12 sixteenths. But you're multiplying that by a 12th, So the 12s simplify out, and you're left with 1/16. This here equals the integral from 0 to 2 pi of 1/16 d theta. And that then is just going to equal the antiderivative of 1/16 is 1/16 theta. So we get 1/16 theta evaluated at 2 pi and 0. You'll end up getting pi over 8. Was there a question there, Marvelous or Dan? Dan's good, okay. Okay, let me see how. All right. Binyam, how are you doing? You doing all right? Just sort of querying people that I don't normally hear from or too often. Naima, how are you? I heard you a little earlier in class. You doing all right? Feeling comfortable? Well, it's a little embarrassing, isn't it, when I call out people and they don't answer, isn't it? It's a little I'll tell you a story. One of my colleagues actually, he was teaching a trig class, and a student was like in the like listed as like attending the class. I guess it was in Zoom, and he started hearing noise, and it turns out the student was attending class on the cell phone, but he was walking around Walmart with his cell phone, I guess shopping during class, and he kind of got caught there, but I don't think anybody here's in Walmart, right? I hope not, right? Maybe give me a thumbs up if you're not in Walmart. Deodath is not in Walmart. Okay, he chatted. Robin's here, Jamal's here. Okay, Eric and John, and good. And you're benefiting. All right. Christopher's not in Walmart. Good. Glad to hear that. All right. Good, Ryan. I'm glad to hear that. Good. Okay. Well, so let me ask you this. Suppose you computed the volume and you got something like this. Suppose you got negative pi over 8. Maybe on the next exam, you're computing a volume and you got negative pi over 8. Would you click submit on that? No, why not? Why not? Ryan thinks not. What's the problem with volume equals negative pi over 8? Very good, Jamal. You can't have negative volume. You can't have negative volume. The volume of the ice cream cone is not negative pi over 8. It's going to be a positive value. And in fact, it's very nice that we can get the exact value, pi over 8, right? Because if we're talking, how much ice cream is being used, we really want to be exact. I mean, the bottom line, margins for food are very tight. And so, you don't want to be off on your volume of product that you're using. Now, what would be nice is if we could verify this result in MATLAB. Well, we can. If we go to MATLAB here, well, let's go into Blackboard. Go into Blackboard here. Okay, so in sorry, not MATLAB assignments, MATLAB programs. Triple integrals and spherical and cylindrical and spherical coordinates. So I'm going to click on that link, And then this MATLAB program will demonstrate how to compute a triple integral using spherical coordinates. So if you click on that, click on the link, MATLAB program there, it'll download the program for, that'll help you here. And then we'll open up that program. Okay, and let's see here. Let me go into the application. Okay, so here's the program. This is triple integration using spherical coordinates. And of course, class, for cylindrical coordinates, I think you can make up your own code for that. But again, it's a triple integral. But this time the integrand is equal to, rho, well, your variables are rho, phi, and theta, right, for spherical coordinates. And your integrand in this problem was rho squared times the sine of phi. That was your original integrand. And so the innermost integral is to integrate the function with respect to rho, and rho goes from 0 to cosine of phi. Next, you integrate the integral with respect to phi. Phi went from 0 to pi over 4. Okay, and then finally, you integrate the integral with respect to theta, and theta went from 0 to 2 pi. Okay, and you notice how I space things out a little bit on these nested integrals. I use like several spaces. Okay, and also you can see how I have the program in the script editor, and in the top right I got a green button. That means no warnings found, the program ought to run. Program ought to run, right? So let's go ahead and, are there any questions? Okay, well, let's go ahead and run the program here. So I'll copy the program. And I'll paste it in command line. I have a split screen here. Okay, I'll hit enter. Look at that. Pi over 8. How many think that's absolutely cool? Naima likes it. Good. 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 Deodath likes it. Wonderful. Yeah, so, you know, I encourage you to use MATLAB to help you verify your triple integrals when you work on sections 12.7 and 12.8. And are there any other questions? Now, naturally, too, you know, class, if you can do a triple integral, by the way, you can write the code for a double integral, right? If you can do a triple integral, write MATLAB code for a triple integral and understand it, you can then naturally write MATLAB code for a double integral. Okay, so, all right, let me stop the recording.